All right, so we're going to look at ticket locks. They are still a spin lock, but they're slightly different. And what we have is, first off, our spinning is going to be read-only instead of using atomic operations. Because what we saw with the atomic operations is that as these CPUs were spinning, they were also constantly sending out these invalidate messages, right? So there's lots of traffic that's happening on the bus. None of that was slowing down the lock holder until the lock holder actually went to release the lock. The second thing we get from a ticket spin lock is we're going to have the waiting order preserved. So this is a form of fairness. So the best model for this would be like a butcher, or if you go to the, let's say, Costco optometrist, then they have you take a ticket. Okay? And the ticket is the order in which they'll serve you. So we're guaranteed that if I've been waiting longer, if I've been waiting longer than you, I'm going to be served before you are. Right? That's the idea of the fairness. And the key idea is we're going to do exactly that. We're going to assign numbers. So when you come to do an acquire, you're going to get given a number. And that's your ticket number, and you're going to wait until your ticket comes up. So here's how it looks. A lock is going to go ahead and have the current ticket and then the next ticket. So this is the next ticket to be assigned. So this is, for instance, when you, again, go to the store and you see and there's a ticket number choose, that's the next ticket. So on an acquire, what we're going to do is go ahead and fetch and increment that ticket. So you get number 34 and the next number is now 35. That's atomic because we have these two operations and they have to be atomic. And then you just sit in loop. You're waiting for your ticket number to match the current ticket number. That's what you're doing. And so in this while loop, all you're doing is reading, right? You are reading lock current ticket and seeing what it is. Read, 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 read. And none of those reads require any messages to other CPUs. And in fact, right, this address is going to get cached. So you're just reading from your cache over and over and over again in shared mode until what happens? Until it gets updated, in which case you're going to be invalidated. And then when you read again, you're going to get the new value. So how well does this work? So we don't have any messages that have to be sent out while we're in the loop, right? The fetch and increment, we're going to have to do a find and then an invalidate, but that's it. So we have this read-only spin. The problem is, as we go and update this ticket, what happens? So it's order one time for the lock holder, right? Because the lock holder is going to go ahead and find everyone else is in shared mode. So what's it going to do? It's going to go ahead and read and then update, which will put it in modified mode and send it an invalidate. So everyone else will get an invalidate. Okay, that's fine. Now they're all in this loop here. So each other CPU got invalidated. So what does it do? Each one sends out a find. It sends out a find before it reads. So when it sends out the find, the first one's going to send out a find, and then the current lock holder will be in M mode, and it will go ahead and then write this value out and then switch into S mode, right? So it's going to send out a find. So let's say CPU 1 is going to send out a find and do this. And then CPU 2 is going to execute this code. It's going to be in invalid mode, send out a find. CPU 3 is going to send out a find. CPU 4 is going to send out a find, and so on, and so on, and so on. So this means we have O of 1 per other CPU. And this is a total then of O of n time, in the sense that we still have all of these other find messages. But the good news is we have fairness out of this. And the other thing we get out of it is we have much less bus traffic, right? Many fewer messages as we're spinning, right? So as the lock holder is doing its thing between the acquire and the release. So this is better, but still we get a total of n squared time to get through all these. So that's bad. So the problem is we're not scalable, right? The cost of handing off increases with the number of waiters. In fact, the cost of handing off we would like, as we said, to be constant. And so let's go look again at our graph. So here's our graph again. So one thing to note is that for this particular graph, the critical section was 7% of the total time. So we go here and we get a collapse at about 9 cores. Why 9? You'd expect maybe 14, right? Because 100, 1 over 7% would be 14. So you expect you can't have a speed up past 14. The problem is once we've got a number of cores waiting for an unlock, all of a sudden, think of it that critical section now is really the critical section plus the handoff time. Or let me put it this way, the serial time is equal to the critical section plus the handoff time. As we get up to about 9, this handoff time starts becoming more. So our total serial time appears to become more like 11%, right? 14% for the critical section plus, 7% for the critical section plus around 4% for the handoff time. So because our slower handoff time also means the number of waiters are growing. So we get this interaction there. So let's do a measurement just of what it costs to do, let's say, an acquire of a lock, followed by just incrementing some variable, followed by a release. So the possibilities are, let's say, we have used the lock last, so not uncontended. Why is it important that we use the lock last? Because that means that the lock is still in our cache. So we're around 40 cycles, 40 nanoseconds basically. If a different core used it last, then our cost is going to be around 100. And then if we have dozens of cores waiting, then our costs increase to thousands of cycles, just because we have that order in cost here for doing our handoff.